We've already done a little bit of vector arithmetic. We've added vectors, we've subtracted them, and we've multiplied them by a scalar. So today we're going to talk about one of the two ways that we can multiply two vectors together. So we have two kinds of products for vectors. We have the dot product and the cross product. So the dot product is section 10.3. So the dot product of two vectors, let's write down what this is. All right, so if we have in R2 two vectors, A1, A2, and B1, B2, if we want to find the dot product of those two vectors, we're just going to multiply component-wise and then add the result together. So we'll take the x components and multiply them, A1, B1, plus A2, B2. So multiply x components, multiply y components, and add them together. And this is going to give you a scalar result. This is why sometimes the dot product is called the scalar product. So you're going to get a number out of multiplying these two vectors together. All right. And in R3, same thing. You're just going to multiply component-wise between the two vectors and then add them together. So A1, B1, then y components, A2, B2, and A3, B3. All right. So let's get some practice calculating the dot product, and then we'll talk about what it might be good for in the next video. All right, so here we have a few pairs of vectors, and we're just going to calculate the dot product. All right, so A dot B, we're in R2 here. We're just going to multiply x components and y components and add them together. So x components, 2 times 3, add together with multiplying y components. So that's going to give me 6 plus a -4, so that gives me 2. All right, and like I said, dot product is called the scalar product because you're always going to get a number, not a vector. All right, so let's try some in R3. A dot B. Let's see, x components, multiply, -1 times 6, and add y components, 7 times 2, and add z components, 4 times -1/2, and then just arithmetic. So let's see, this is -6 and 14. 4 times -1/2 is going to give me -2. And let's see, that's going to leave me with 6. So our last pair of vectors is written in the IJK notation. So if you absolutely hate the IJK notation, you can rewrite those in component form. That'd be fine. So we just write down the coefficients of the IJ and K. So 1, 2, -3. And B has no I written there. That just means the I component is 0, 2, -1. Absolutely not necessary. Just go with whatever notation is more comfortable for you. Okay. Dot product. So A dot B, multiply x components, add, multiply y components, add, multiply z components. And I get 0 plus 4. That's going to give me a +3, and I get 7. All right, so dot products are really pretty straightforward to calculate, just multiplication and addition. The last thing I want to do in this video is show you some properties of the dot product. So our first property of the dot product is that it doesn't matter which order you do it in. Okay, so A dot B is the same thing as B dot A. You know, if I do 1, 2, dot 3, 4, that's going to give me the same result as if I do the 3, 4 first and the 1, 2 second, okay? Because all you're doing is multiplying, which can happen in either order, and adding after you're done. Second property I find to be kind of reassuring, and that is that the dot product will distribute over vector addition. So this looks a whole lot like number multiplication, and the dot product is a kind of vector multiplication. So if you're doing A dot B plus C, you can distribute that A over the B and the C and then do the vector addition, and you get the same answer. Our third property says that if you're going to do a dot product and then multiply by a scalar, notice that n does not have that vector bar above it, so it's a scalar. So think of that as like the number 5. So you're going to do a dot product and then multiply by 5. You could instead, if you wanted to, scale up the vector A by a factor of 5 and then do the dot product, or you could scale up the vector B by a factor of 5 and then do the dot product. You just can't do that 5 multiplication times both vectors. You have to pick your favorite. Our last property is a particularly useful one, and that is if you dot a vector with itself, that's the same thing as finding the magnitude of that vector squared. Okay, and that looks a little bit odd, but let's think about why this would be true. So if you have a vector a1, a2, and you dot it with itself, a1, a2, you're going to get a1 times a1, which is a1 squared, plus a2 times a2 squared, right? And that's exactly the innards of the magnitude formula, right? Magnitude of A is just the square root of that stuff right up above, right? A1 squared plus A2 squared. So if I were to square both sides of the formula for the magnitude, I'd get that the magnitude squared is equal to the same thing I got when I dotted the vector with itself. So that's it for properties of the dot product. In the next video, I'm going to talk about what the dot product is useful for.